Hello and welcome to problem 14 in my Calculus 3 or multivariable calculus problem solving series. In this video, we're going to look at how to solve double integrals using polar coordinates. So sometimes when we take the double integrals over regions, there's no easy way to describe the region using curves. But if we use polar coordinates, then the integral becomes a lot easier and we can solve it. So how do we use polar coordinates for double integrals? Well, remember that polar coordinates, instead of having x and y as your inputs, you have radius and theta, your angle. And this will give you a region in 2 dimensions, which is where you're going to take the double integral of. So you're going to have R1 and R2, and this is going to be the change in radius, and then you have theta equals A and theta equals B, which is how wide the angle is opening. And then we want to find a small piece of area. Just like we did in the previous video, the small piece of area, dA, was dx times dy. But for polar coordinates, it's going to be a little different. Because if we take a look at one of these small pieces, it's not actually a perfect rectangle. But we know that this side of the rectangle is a change in r. And the right side of the rectangle is a r times a change in the angle. And this is similar to what we've seen in previous courses, where for polar coordinates, where dA is going to be r times d theta times dr. So we see that here. And this is what we're going to use for the double integral. So when we're taking the double integral, we need to swap out all of our x's and y's for r's and thetas. So it's going to be the integral from r1 to r2 for our radius, the integral of from theta equals a to theta equals b of f of r times cosine of theta, comma r sine of theta, because r cosine of theta is equal to x and r sine of theta is equal to y. And another important conversion that you should know is that r squared is equal to x squared plus y squared. And then we're going to multiply that by the r, since we have remember that dA, our small elements of area, is equal to r times dr times d theta, and that's what we see here, r d theta dr. So this is what we're going to use to solve our integral for these special regions. So let's go ahead and look at an example. Here we have a surface f of x, comma, y, which is equal to e to the power of x squared plus y squared. And we want to evaluate the double integral, or find the volume, of this surface over the region of the unit disk with radius 1. So it's this disk centered around the origin that has a radius of 1. So let's define our bounds in terms of r and theta. Our bounds in terms of r will be from 0 to 1, because the radius will go from 0 and it goes all the way out to 1. And this will give us the radius for a disk. The bounds on the radius of a disk. And the bounds for the angle, theta, will be from 0 to 2 pi. And then this, so the angle starts at 0 and it goes all the way around to 2 pi. So our integral is going to be the integral of our function e times r squared, because we swapped out x squared plus y squared for r squared, times r times dr d theta, where the bounds on r is from 0 to 1 and the bounds on theta is from 0 to 2 pi. And then we solve this like any other double integral, where we have the inside integral turns into 1/2 times e to the power of r squared, evaluated from 0 to 1. And this equals 1/2 times e minus 1. And remember, we still have that other integral in there from 0 to 2 pi for theta. And we're just going to multiply 2 pi into this, and we get the answer equals pi times e minus 1. So this is what the volume of our double integral will be. So that's all for this video. Thanks for watching.